Yeah, so we have just started the local regression. So the idea of the local regression is to use just local information so that the model is more flexible. So yeah, so so think about the example. So we have the X. Yep. So we have the X-axis and Y-axis. And then we have the data. Data is denoted by the blue crosses. And this has the somewhat complicated pattern. So probably the trend line is like this. If we use a straight line, then we cannot describe the relationship in detail. So if we make this line, then so at least around here that we have the negative bias. I mean positive bias, I would say. This red line is above the blue points, and also around here we have positive bias, and here we have the negative bias for the estimate. But if we use only local information, so suppose that we have this point and this point, this point, this point, we have, if we use local information to fit the data, then we have more accurate estimate for the observations around here, this orange circle. So that is the idea. So only we use the similar information to each point X. So suppose we have the X naught here, then we only use the observations around X naught to estimate the fitted value at X0. Yeah, so given X naught, a simple function that typically a straight line is fitted only with a certain proportion of observations. For example, the 20% of observations, which are close to X naught. Also, observations closer to X naught are given the higher weights. So even we have only 5 observations here, if the observations are closer to this X naught, we give higher weight. So think about the case that we have X-axis and we have X naught, and then we have the 5 closest observations. If one observation is here, the one observation here, and one observation here, one observation here, one observation here, then we have the higher weights, higher weight for this observation, or maybe this observation, and for this observation, we give the lower weight, so that we can calculate the fitted value for X naught more accurately. Yeah. So this is the idea of the local regression. Yeah. Yeah. So and yes. So what's the proportion? What proportion we have to take? So the proportion have different meaning. So in one extreme, suppose n is equal to 100, and suppose s is equal to just 1%, 0.01. Then if we take 1% of observations, 1% of closest observations to X naught out of 100 observations, that means that we just choose the closest observation, just one observation. So fitted curve is as volatile as the original observations. And if we have S is equal to 1, that means that we take all observations. So that means that we just fit usual linear regression. So this is the two extremes. These are two extremes. So we should go somewhere in between. If S is small, it's more flexible, but sometimes it overfits the model. And if S is closer to 1, it's less flexible, but we have smaller risk of overfitting. Yeah. And of course, we cannot estimate the fitted value for all possible x because we have infinitely many x on x-axis. So there are, yeah, so typically we estimate the f hat of x for each observations x. Okay, so suppose we have 100 observations, and okay, so x is equal to maybe the 1, 3, 5, 7 up to 199. We only calculate f hat of x for these x values. So this is one typical way to calculate this fitted line. So theoretically, we can do we can calculate f hat of x for all possible x, but in reality, we can only have to pick we have to pick our finite number of x. Okay, so this is the illustration. So yeah, so either yeah. So I don't know the parameter, but okay, so these are observations. Both the red circle and the blue circles are observations. How many observations in one graph? I'm not exactly sure. Maybe 200, a little more than 100. It looks maybe 100. And maybe, I don't know, n is equal to 100 and s is equal to 0.25, maybe. I don't know. So if we pick up this point, then we choose 25, the closest observations. Maybe 10 observations. How many observations? Yeah, it looks 10, sorry. It looks 10. So maybe n is equal to 100 and s is equal to 0.2. Yeah, so we choose the closest observation, 20 observations, and using these 20 observations, we fit the straight line. But we give higher weight for closer observations. And this green curve represents the weight given to each observation. For example, this observation, it's close to this x0, so it's given higher weight. Okay. This green graph doesn't have a weight, doesn't have a scale, but the highest weight. And okay, so this observation, maybe okay, so for example, this observation is far away from the center, so we give only the small weight for this one. So okay, so in linear regression, that we take the summation of, so we minimize the sum of the squared errors. So the sum of y I hat minus beta naught minus beta 1. Sorry, this is y I hat. So the yi minus beta naught minus beta 1 xi, we minimize this quantity, but we put some weight. So we have the wi here. Okay. So we minimize this quantity. And this wi is given by this green graph. So this is the wi. Okay. Yeah. So you can see that okay, so this is almost this point. This x0 is almost the left end of the data. Okay, so even if we pick up the 20 closest observations, most observations are larger than x0. So if we just give the same weight for those 20 observations, basically it's affected more by these observations, but we want to have the local information around x0, so we give lower weight for these points. So still, we fit the straight line. So even we don't put weight, still it works somewhat well. But okay, so if we think about the even simpler model, we just fit the straight line. We just fit the constant on these 20 observations. Okay, then probably it has a positive bias. If it has a positive bias, if we fit this model, because the x0 is the what should I say? So the most observations that have the larger x value than x0, and also larger y value than this point. So that means if we take just average of these 20 observations, that means that we fit the constant function to these 20 observations. You can see we have some positive bias, right? So even if we fit the straight line, if the situation is a little bit complicated, then it can generate bias. So we use mostly around these observations to fit the value. So if we don't give a weight, we have higher risk of having a bias. So that's why we put higher weight on the observations close to x naught. So that is given by Wi. So this green curve looks the normal density function. So in this example, probably the Wi is given by the exponential of negative x naught square, so x minus x naught square. So I will say xi, sorry, xi minus x0 square over 2 or something like that. So if xi is closer to x naught, then we have higher Wi. Far away, then we have smaller Wi. Yeah, and here that we have different x naught, and still that we have the closest 20 observations. Oh, I think that the proportion is higher here. Yeah, it sounds that we took 50% of observations here. So maybe this regression model and this regression models are different. So this is S is equal to 0.2. This is probably S is equal to 0.5. So these are different estimations. It looks the data are the same, but these are two different estimations. And the right pane that we set x naught as here. So we choose the 50% of observations here. Then we fit the straight line here. So we have slightly negative slope. Then fitted value is this, the orange circle. Yeah, so this is how local regression works. So for example, if we want to know the temperature trend because of global warming, probably you don't just fit the straight line in the past 2,000 years of data, right? So probably we will pick up just the maybe the data after 2000 or something. So that is basically doing local regression in some way. So we just see the somewhat the recent situation to fit the data set. Or if you want to calculate the maybe the population growth in 1970s, then sorry, what should I say? Yeah, population is not random anymore, but yeah. So for example, if you want to see if the temperature, the World War II affects the temperature, then probably you will take some observations just around those periods to fit the straight line, right? So that is basically a similar idea to local regression. Maybe that has some more specific meaning for the time period, but yeah. So the point is that yeah. So maybe better example is that yeah, if you want to take some health advice, then probably you want to seek an advice for the people similar to your age or your the body measurements and so on. Yeah. So yeah. So this is the formulation. Oh, do you have any questions? Yeah, so the procedure to estimate f hat of x naught for each x naught is at first we take the proportion s of all observations, so 100s% of observations which are close to x naught. And if x1 to xk are such observations, the x values of such observations, that we will give weight by this the k of xi x naught. And the k of xi x naught may be given as our normal density function in the previous example. Yep. Yes. Yeah, so what k we should use and what proportion we should take. So that really depends on the analysis. So those are hyperparameters. So we have to optimize it in some way. Yeah, so this is the local regression. Yeah. Yeah, so local regression is really necessary in some cases. So in the past, I did the sample survey when I was working for a bank. And we just have the data of the businesses about their sales and profit and so on. And okay, so think about some sales of the data. And okay, so suppose that we have the 10 companies and yeah, so maybe the number of employees here. And this is sales. And we would like to take the average, the sales amount. Okay, so then suppose the 10 observations are like this. Okay, so more, I mean, the larger companies have basically larger sales. Okay, so 4, 5, maybe like this. Okay. And to estimate the, yeah, so suppose that we ask all of these 10 companies about sales, but only a few of them answered the survey. And if they have more employees, then they are more likely to answer the question, right? So if you send out the survey to businesses, and if the company have only 1 or 2 employees, usually they don't have enough time to answer it. If there are 10 employees or even 1,000 employees, maybe they have some, customer relations department or investor relations department. So they will respond to the survey with a higher probability. So the typical case is, okay, so these companies answer the questions, maybe this and this, something. Then if we take average, then basically we overestimate the sales. So this is the observed average, the average of answered, the replied company, average sales of. Which replied. So this is a problem if we just take the average. Okay, so, and this problem does not solve even if you separate the strata. So suppose that we have, okay, so maybe the larger company and the smaller companies are different, so that we set 2 strata and we separate these 2 surveys. But still, you can see that these companies answer the survey, so it overestimates the mean a little bit. And here also, slightly larger companies maybe answered the question. So still the sales for each strata overestimate the average sales in each group. So in this case, probably that you have to fit the straight line to get more accurate sales. For example, if we think about the average number of employees, maybe this is the X naught, and we fit the straight line. Then even if we have only, maybe this is not, so if we only have 6 observations, probably we can more accurately estimate the average sales of the entire 10 companies. So if you use a straight line for the local information, then we can estimate it more accurately. Yeah, do you have any questions about local regression? So this is a very intuitive idea. So we use local information, similar information to our objective. Then we can get a more accurate. I mean, we can get the. I would say we can get the estimate which is less biased. Okay, so far that we have only one predictor X and one response Y. So now we think about the multiple predictors X1 to XP. Right. So yeah, so this case the model is more complicated. For example, so Y is equal to beta naught plus beta 1x plus beta 1 x1 plus beta 2 x2 plus epsilon. But sometimes relationship is not linear. So beta 1 plus beta 1x plus beta 1 x1 plus beta maybe beta 1 1 beta 1 2 x1 square plus beta 2 maybe square root of x2 plus epsilon. Or even more complicated models such as y is equal to beta naught plus the beta 1 1 x1 plus maybe beta 2 times root square root of x2 plus beta 3 times x1 x2 plus epsilon. So the much more complicated than, so the situation is much more complicated than just one variable. And generalized additive models that deal with these models. So basically x1 and x2 are separated. We don't think about the interaction between these two terms, but we calculate the more, we consider more complicated relationship between y and each of xi. So yeah, so the model formulation is here. So yi is the constant plus the summation of fj sub xij plus epsilon I. So I is the index for observation. So the j is index for the variable. So j is equal to 1 to p. So we think about the fj of xj. So generally some function of xj. So typically polynomial or spline or so any function. But yes. So but we assume that the interaction does not exist. So we don't have the term such as x1 times x2 or x1 times x3 times x5. We don't have those terms. So just summation. So we need some simplification at least if the situation is complicated. So this is called the generalized additive models. Yeah. So yeah. So fj is, for example, estimated by smoothing spline. Yeah, we can take fj is equal to polynomial, but that is just in a class of linear model. So we can make xj as smoothing spline. So this is one example. So this is yeah. So we fit the wage on year and education, and age. So wage is y, and year is x1, and age is x2, and education is x3. So when we fit the y on function of x1, function of x2, and the function of x3, and we see just profile of that function. So basically we fit y is equal to, okay, so f1 of x1, maybe we have the intercept. So y is equal to maybe beta naught plus, yeah, this plus f2 of x2 plus f3 of x3 plus epsilon. So then we make a graph of y is equal to f1 of x1. Yeah, maybe y hat is equal to f1 of x1. So so this is the graph of f1 of x. So you can see the year, what is the year? Yeah, year is the year that the wage is observed. So the wage is going up over years. So that in 2003, on average, this is -5. I don't know the scale, but the -5, and the so on average this is 0 because we include intercept here. So on average 0, and in recent years we have higher average, 2008 or 9. And also age. So we have seen that the age between maybe 35 to 50, that we have higher wage than other people. So that we can see this complicated curve. So basically, the wage goes up more rapidly from the year 20 to 40 because of the education they have taken or experience that they have accumulated. So then after that, gradually it goes down. I don't know, we have some bump here and what happened. But yeah, so this is the curve. This red line is estimated F2. So F hat is equal to F2 of X2. Then the third one, the education. So education is actually the discrete variable. So we only have the 5 possible values, maybe less than high school, some college, and maybe more than college, graduate school. Then the wage. So this is just categorical. So these are I think similar to box plot, right? So that we have some range and the average. So this is y hat is equal to F3 hat of X3, but X3 is the discrete. It can take only 5 values. So the answer is also discrete. Any questions? Any of you have used the GAM before? Hello?
Nope, I have not used it. Nope.
You haven't? Anyone from engineering or no? Yeah, actually personally before personally I haven't used it too many times, but
Sorry,
yeah, you can
Professor.
see this is pretty useful.
I have a question.
Yeah.
For education level, why do we have boxes? Because I think they all of them should be just 1 point, not boxes, because they don't have range. It's a certain point.
Sorry, what the band you mean?
Yes. What are the bands for?
Oh yeah, I think that this is the same as the dotted line on these 2 figures. So this is the confidence interval. The probably 95% confidence interval.
I see. Thanks.
Yeah. So yeah, that's a good question. So the yi, so we have the yi is equal to F3 hat of X I3 maybe. Then we have, okay, so this is basically the linear model. So that means we have coefficient for each level, right? So yeah, so baseline is the high school graduate. So the baseline is the intercept, and the difference between the so the high school, so the high school and the less than high school, and we have coefficients. And college equal college. So coefficient 1.1, 2.2, 3.5 or something. Then this is the standard error. So 0.5, 0.7, 0.7. I think that this should be the, anyway. So yeah, then I don't know, maybe ±2 standard error is written here. So the estimate is just 1 point, yes. Okay, and the width is represents the sample size for each class. So this graph, this data have the more high school graduates and the some college graduates and some people just drop out in the college, and a smaller number of less than high school or graduate degree. Okay. Yeah, so this dotted line is more complicated probably because the we fit the straight line, fit the some curve, right? So the probably this is by the spline. Then they calculated the confidence interval in some way that is the dotted curve. If straight line, it's not difficult to get the you know, the confidence interval. Confidence, I mean the probability. Oh, I see. This is, I think, the confidence band. So yeah, for straight line, we have studied in 50-30 how to make the confidence band, and the spline. That also we can do it in some way. Yeah, and GAMs is available for classification also. So in classification, basically we fit the probability of y is equal to 1. When we set the probability of y is equal to 0 as p of x, then this one, so this is basically the probability of y is equal to 1 over probability of y is equal to 0. So the ratio, and then we take the logarithm, then this is in the negative infinity to positive infinity. So we fit this probability on these functions. Then we can represent more complicated cases. For example, if we have x here, and this is the probability of y is equal to 0, then the curve may be complicated, more complicated. For example, I don't know. Yeah, for example, the probability that okay, so this is maybe age, probability that each customer buy a bike, motorcycle, then maybe, you know, probability is very low until age 15 or something. Then after that, it goes up dramatically. Then after that, maybe 30 or 40, we have lower probability. But once people are retired, then the probability goes up again and then goes down or something. So if this kind of complicated relationship between x and the probability of y is equal to 0, that we cannot use logistic, you know, just the one logistic regression, right? So that we have more complicated curve. We need more complicated curve. So that we should put the f1 of x and so on. And if we have multiple factors, then we have f1 of x1 to fp of xp. So similar to polynomial regression, the idea can be applied for binary regression. Okay, so this is chapter 7. So now we discussed how to schedule the final project. So I don't know how many of you are here. 1, 2, 3, 4, 5, 6, 7 people. So I think the 2 people are not here. So I'm thinking the final presentation on April 21st and the 26th. And I think that 21st is Wednesday. And the 26th is on Monday. And possibly 28th also. 28th is Monday. So we would like to schedule it on those days. Yeah, so 21st. Yeah, so I'm thinking that to put maybe 5 students on 21st and 4 students in 26, and we just finish before the final exam period. But if you really want to make a presentation at a later date, then we can split into 3 days. What do you think?
Anything works for me. I think it'd be nice to get it done earlier though, so we can, stress about other exams and whatnot.
Yeah. So my concern is that in the past, the students who couldn't finish the final project is the final project assigned during the final exam week. So they are too busy and they couldn't make it. So I think that it's better to make it earlier, but still, different students have different, scheduling. So any other people who want to do presentation on 28th? Okay, so now maybe we will ask which day do you prefer? 21st is a little earlier than 26th, so I don't know, but I see. I didn't really. Yeah, I think I have to finish the grading the quizzes, but maybe the Walid, are you here?
Yes, I am here.
Can you make the presentation on the first day? Is it possible?
Yeah, that's fine. That's okay.
Okay. And if your presentation date is earlier, then I will comment your final project plan earlier. And how about the Vahid? Can you make it on 21st? Is it possible?
Well, actually, I prefer 26 if it's possible.
26, okay, I see. And how about Andrew? Andrew is not here. Still, he's not feeling well, maybe. Okay. Ian is here.
Hey, Professor, I'm here.
Oh, can you make it on 21st or?
I am moving to Chicago on the weekend of 4/17, so I'd really like to have a couple extra days. The 26th would be much easier better? For sure.
Okay, I see. Okay. And maybe I would, so Andrew is not here, so maybe I put Andrew here. And yeah, 20 for lead, Andrew, Jacob. Jacob is not here. Oh, not here today. Not here today. Maybe I will assign Jacob on the first day. So he made 2 presentations in my class in the past, and he did very well. So probably the first day is a good choice. And okay, so for others, any preference? For example, I think the Caitlin and the Catherine, Raymond, Colin, which day is the best for you?
This is Catherine, and I would prefer the 26th if possible.
Catherine, if possible. Okay.
Yeah, thank you very much.
Anyone else?
I would also prefer the 26th if possible, because I have a presentation on the 20th for another class, but I can move if no big deal.
Okay.
Or I mean, if it's a big deal,
Okay, so I don't know, in the bracket. And the others, Raymond and the Caitlin, do you have any preference?
Hi, I guess I can go with the 21st.
21st, you're Caitlin, right?
Yep.
Yeah, I can go 21st as well.
Okay. Okay, so yeah. Okay, so just the way, at least for now, that we decided this schedule. Yeah, and the presentation will be, I'm thinking 12 minutes, 30 minutes. Also, I have a question. So do you have any schedule after this, the Monday, Wednesday, 7 to 8:15? Is it a problem if we extend the lecture for like 10 or 15 minutes on those 2 dates?
It's not a problem for me.
Not a problem?
Not a problem.
Okay. Yeah, you know, presentation, sometimes not everything is on time. So if anyone has trouble, then at least I will put that presentation at earlier time. But okay, then that's good. Okay, so then we try to finish in those 2 days, and I think it's doable. Only 9 students. In the past, sometimes 30 students make a presentation, and I really have to use the final exam period. But yeah, that's it. Okay, so great. Yeah, I will send this schedule to you by email via Canvas. Okay, so okay, so now that we go to the chapter 7, the 7 lab. So you can see these slides in Canvas, so you can check it. Okay, so yeah, we have many materials to study here. So first one is polynomial regression. So basically we cover all examples of chapter 7. The polynomial regression, so the data is here. So often the time series data is a good example to apply the polynomial regression, because we have some complicated pattern. So this is the Nile River water level data. This is annual data from 1875 to maybe, I don't know, maybe 1870 to 1970, maybe. And you can see that the water level is higher until maybe 1900. Then after that, it gets lower. Recent years, possibly slightly higher. So like this. So it's not very simple trend. Oh, sorry, the 1871 to 1970. Okay. Yeah. So this is in the default package. Yeah, so I don't know. If just you start R and you type Nile, then probably you can get you can get the data. So this is the in default R package. Okay, and yeah, time is time. Yes. So yeah, so linear regression. If we fit the Nile on time, so that means that we assume the linear trend. I don't know what's the curve, but maybe like this. Oh, sorry. This is a problem. Okay, so this is the probably the fitted line. So this is the Nile is equal to beta naught plus beta 1 times time. So linear trend. Then we can get the coefficient as usual by LM function, and the t-value negative 5.2, p-value very small, so it's significant negative trend. So now that we fit the polynomial regression with degree 2. So basically y is equal to beta naught. I mean the y is Nile, and x is time. And so this is one simple way to put polynomial regression, but here we have different bases. So basically beta naught plus the beta 1 times I would say maybe S1 of x plus the beta 2 times S2 of x. And S1 is actually the straight line, and S2 is a quadratic function, but the S1 and S2 is orthogonal. Actually, to be accurate, this one. So that we fit this. So this is the S1 of x. So this is x1. And this is S2 of x. This is x2. So actually the correlation between x1 and x2 is equal to 0. Correlation is almost 0. Negative 1 times 10 to the power 16. So this is almost 0. Okay. So yeah, so in this way, we can separate the effect of two variables, the in a better way. So if we just use the x and x square, then this red curve is like this. And this is somewhat similar to black one, right? So it's not very convenient. Sometimes that we have multi-collinearity between two curves. And also the x square becomes too large when x is large. Maybe 100 square is fine, but if that becomes maybe 1000 cube or the 1000 to the 7th power, it's too large. So it's good to use the orthogonal basis. So that can be done by this polynomial function, poly time 2. So this is the straight line, and this is quadratic curve, but these are basically orthogonal each other. The correlation between the first component and the second component is 0. And the t-value, so these are really significant. And actually, it's harder to interpret these coefficients, but at least this means that the two terms are both significant, so probably it's worthwhile to have the two terms. And also the second one, only second one include quadratic term. So the quadratic term is useful to improve the model. So the first, the straight line. So this indicates that the slope is significant, but the second regression result says that the quadratic term is significant. So probably it's good to have the two terms. But if you want to stick with beta 1x plus beta 2x square, then we can also do that. So this is the same result. And if you want to do this model, so y is equal to beta naught plus beta 1 plus beta 2x square plus epsilon, we can do that in this way. So polynomial time, the 2 rho is equal to t. Then we don't use orthogonal basis, but we use this x and x square. And the estimation result is here. So this is x. Okay, so this is x, and this second one is x square. And what's the coefficients? And okay, so this is the coefficient, and this is the t-value. And sorry, this is standard error, and this is t-value, and this is the p-value. So you can see the both are very significant. So t-values both larger than maybe 2. And yeah, the x is slightly less significant here. So last time negative 5.5, maybe negative 5.6. Yeah, so it becomes negative 4 because of the collinearity between these two terms. So this is negative 2.89 to the, so negative 289, and the standard error is here, so 72. Previously, this was the negative 784 and the standard error 140. So yeah, I don't know how to interpret it, but yeah, I think it's hard to interpret this, but at least it becomes less significant. So so this is x, so easy to interpret, but this is yeah, function of x, and yeah, so this is function of x. So this estimate itself doesn't have much meaning, but at least it's more significant in the previous one. Yeah, but the fitted values are the same. Fitted values are the same. So even if we take different bases, then in total we have the same thing, right? So suppose that the fitted model here is the y is equal to 1 plus 2 times x1 plus the 3 times x2 plus epsilon. And previously we fit the orthogonal basis, so that becomes maybe 1 plus I don't know, maybe 3 times maybe x1 minus 2 or something, and a plus x and x square. If the function is this, then the other fitted function is this, and maybe 3 times x squared minus 0.33 times x, and minus 6 plus 1 minus 5. So 1 minus 6 minus 5 plus 6 plus 2. Okay, so we use just different bases. So x and x squared, or just one linear function of x and one quadratic function of x. But if you simplify this, basically it becomes the same thing. So this becomes x cubed, and the constant term is 1 minus 6 plus 6. So this is 1, and plus negative, positive 3x minus 1x. So this is 2x. So basically we have the same model, but in a different expression. Okay, so in this way, yeah. Yeah, so another way to use the same model is this. So this is maybe more straightforward, nil on time and the square of time. So if we include the square of time, then you have to put I. Yeah, so this is just our format. So if you want to just see the square of time, then you can just type the time square. But if you want to put it in a LM function, then you have to put I parentheses. And the reason is that actually the multiplication has different meaning in LM function. In LM function, if you write the x times z, so this means the term of x and the term of z and the term of x times z. So we have the 3 terms. So probably they want to distinguish these two. So x times z in LM function means these 3 terms, the 3 predictors. So probably they want to distinguish this with just the component-wise product of x and z. So this in LM means the 3 vectors. Okay, but anyway, so you don't really have to care about the reason. So inside LM function, always you have to put I. And we got the same result. Then we can do this 3rd degree, 4th degree, 5th degree polynomial. So these are orthogonal bases. So we have seen. So if you put the rho is equal to t, then this becomes the non-orthogonal basis, x squared, x cubed, and so on. But we don't specify this, so the polynomial means the polynomial with orthogonal basis. It's similar to this case. So red curve and the black curve, black line, these have the basically 0 correlation. Okay, so these are polynomial, also polynomial 6, 7, and I just overlaid those 7 figures here. So yeah, the legend isn't really in the pane, but the black one is just a straight line, and the red one is quadratic curve. So it's really hard to see, but the red curve is probably comes here, right? So no, this is not. This is pink. So probably like this, right? So this is the second one, and the third one is cubic curve, and the 4th one, 5th one, and so on. So yeah, I don't know which is the correct one, but it changes a little bit. And if the degree gets higher, actually it doesn't change much. So first several ones are different, maybe 1, 2, 3, 4 are different, but after that probably it's pretty similar. Maybe. Yep. And now we want to see which is the best. Of course, we have more terms, more predictors. It adjusts to the data. It fits to the data. So the error is smaller, but the variance becomes larger. So bias is smaller, but the variance becomes larger. So if we use AIC, we can evaluate which is the best. And it seems that the power function with degree 4 is important, because we have the large decline from third degree polynomial, from third degree polynomial to fourth degree polynomial. After that, actually, it doesn't really matter. So fifth and sixth probably almost useless. And the seventh, it's a little better, but the AIC level doesn't go below the level of the 4 variables. So probably the 4 is reasonably well. And of course, we didn't see there are more terms. So maybe, possibly 8, 9, 10 or something, but probably not. Maybe like this. So AIC, if you use the p is equal to 4, then the model is reasonably good. So for 4 degree polynomial. And this is ANOVA, so test. So we put all models. So this is the polynomial with degree 1, degree 2, degree 3, up to degree 7. Then we can see this sequential table. So this means that the degree 1 to 2, this is the significant improvement. And also you can see the 3 to 4 significant increase. And actually the 6 to 7 also significant, but others are not really. So the 2 to 3, or sorry, the 2 to 3, or 4 to 5, 5 to 6, not really significant. Yeah, so at this point, probably you would go with 4, possibly 7, but 4 may be enough. Questions so far? Oh, this is useful way. Maybe we have done this before, polynomial. No, in earlier chapter. No, maybe 50-30. I don't know. Yep. I think in some homework in either this class.
I think the midterm we used.
Polynomial, right?
Yeah, polynomial. I think it was for time. I think it was for the Old Faithful question.
Oh, yeah. That's true. Yeah, you applied polynomial at least. Yep. Thank you.
And also for the, I think it was the air quality one where you had the x1, x2, and then there's the x1 squared, x2 squared as well.
Oh, yeah. That's also done here. But yeah, that's right. Yeah, but in this section, in this chapter, yeah, so we go just the more complicated relationship between y and one single predictor x. Yep. Yeah, so practically the interaction terms are important also. Yeah, so yeah, I didn't see your faces, so just I want to make sure that everyone listens to the lecture. Okay, so I know that the Vahid Raymond is always online. Yep, and the next one is logistic regression. So sometimes we can dichotomize the variable. So basically, we assign 1 for here and a 0 for here. Okay, so 1. So we want to see if the water level exceeds 1,000 or not. Yeah. So you can see that the more observations here exceed 1. Right, so around here, maybe I would say that the more observation exceeds here. Also, maybe possibly around here. Here, maybe lower probability. So the different time have different probability to exceed the 1,000 maybe millimeter. So in this case, we can use the GLM for the logistic curve, and this is just the y on time, so Nile on time. So y is the this indicator variable. And we can also use the polynomial within the GLM function, and the polynomial with degree 3 also. So first one, just the time, we have negative coefficients significant. So that means the probability to exceed 1000 millimeter goes down in recent years. AIC is 106. And the next one, then we have the two terms. And this is maybe marginally significant. The p-value is 0.09, so marginally significant. So quadratic term may be useful. It's a little harder to interpret this. Yeah, so possibly, probability is like this. So it's slightly going up in recent years, or possibly not, but we have the large drop in probability in earlier years. Then also this becomes quadratic curve. Yeah, so if you want to see what's the quadratic curve, then you can either plot or you can use the row function x and x squared. Then you can see what's the fitted function. And the third degree polynomial, we have 3 terms. And these are t values. So yeah, quadratic term is maybe significant here, but the cubic term, probably it's useless. So either we go the degree 1 or degree 2. AIC is 107.35, 105.58. So in terms of forecasting, the 2 degree is the best. So p is equal to maybe d or 3. P is equal to 2 is the best. So 2 degree polynomial. Yeah, so AIC we can compare. So probably this is the best. Okay, so next one is the step function. So that we want to fit the step function on the Nile data. So we have, so we have data, but we fit the maybe level, this level, this level, this level, and this level or something. And the point is where to put the knot points. So knot point, maybe C1, C2, C3, how to put these knot points. And the one, simplest way is just the cut data into 4 equal parts. So that can be done by this cut function. So the time includes 100 time points. So in this case, just the equal interval sequence from 1871 to 1970. But just we cut this into 4 pieces of 25 observations. So in this case, actually all intervals have the same length, but in general, it depends because in some area we have more observations. Okay, so now we just so basically we divide the data into 4 equal pieces. So 1871 to 1895 and 1896 to 1920 and 1921 to 45 and 46 to 70. So we have these 4 pieces. And we can just put this cut time to function in Nile. Then we can fit the data. And also that we change this 2 into 2 to 10. So we can have more knot points. Then this is the fitted line. So this the red one. Red one is the 2 pieces. So the 1 knot. And the green one is 3 pieces. So this is 2 knots. And the blue one, we have the 4 knots. 3 nodes, 4 pieces. Okay. And yeah, I didn't put more because it will be too crowded if we put more. And if we compare AIC of the 2-piece and the 3-piece and 4-piece, what's the best? Actually, this one is the best. So at least the 4 pieces are better than 2 or 3 pieces. If we increase, actually, but it does not increase the accuracy. I mean, it does not improve AIC. So smaller AIC is better. So probably 4 pieces, 3 nodes is the best. So 10 means 9 nodes. So of course, we have optimal node points, right? So sometimes if we increase the number of nodes, then the nodes move to the not optimal points. So that's why the AIC decreases, and even the fitted value could decrease. But in this case, the 4 pieces is optimal, it sounds. But this is just equal for intervals. So if you optimize it, then it can possibly be better. So okay, so look at this graph. And you can see that in the first 20 years or so, that we have the higher level of the water. And the second piece probably much lower, but still higher than some point. And this is the almost outlier, and outlier affects the likelihood and AIC a lot. So probably this outlier, maybe we can separate it. That is the better way. And after that, it's almost flat. So if we set the 4 interval in this way, maybe first 25 years and the next 15 years, then just 1 point and the remaining period, probably the fit becomes better. So this is arbitrary, but I defined the 4-step functions in this way. Then we fit. So we have 4-step functions, but that we have the intercept. So we should omit one to avoid the identification problem. Then then this model actually achieves the AIC of 12,000 and 51. So this is much better. So this is 1,270. So the decrease is 19. So this is very large. One reason is that we have the 3 nodes point, not 3 nodes in arbitrary points. So 3 nodes, basically 3 parameters, right? So basically this decreases AIC by 6. In AIC, the penalty is 2 for each parameter. So if we have 3 parameters, maybe I should say the 3 parameter increase the AIC by 6. Right? So 3 times 2. But actually it did not, because the before fitting line that we arbitrarily defined that is 3. So it should increase AIC by 3 by 2, but actually we didn't count it. So maybe the fair comparison is this plus 6. Okay. So 1 to 5, 7. 1 to 5, 7. So this is probably a fair number to compare with this lowest AIC. But still, it's much lower than 1270. So probably if we optimize these parameters, then we have a better model, actually. But
sorry, Professor. Why we didn't consider that 6th parameter in the AIC?
Because of just the code has some problem. Because when we fit this model, we just hand-picked 3 nodes, and we defined S1 to S3. And then we put these 3 variables in LM function. So R doesn't know that we optimized these 3 nodes. Right? So we manually picked the 3 knots.
Yes, I see.
Yeah.
Thank you.
Right. So if in the R procedure they optimize these 3 parameters, that they can recognize there are 3 parameters, but the R does not recognize 3 parameters here. So the AIC is artificially lower by 6. Yeah, so that's it. So it's hard to choose the knots, right? So if we do all combinations, then yeah, certainly that we can optimize it. But yeah, and okay, so this is the fitted line. So this is ad hoc, but you can see, that it fits better. It fits better. Yeah, but this is arbitrary. Okay, so that's it. And okay, so next time that we do the basis functions and the regression spline, smoothing spline, and the GAMs, and so on.